I'm trying to remember because I was waiting for you to finish. But
Sorry.
I did have a question regarding the calculations for and the mechanisms. That's what it was. The mechanism. So
there was no mechanism presented in this experiment. So when you go to experiment like 13, you see there is a mechanism for esterification, then you copy the mechanism. For this reaction, for this experiment, there is no mechanism, and there is no need to include the mechanism. That
I
part?
thought,
Yes.
yeah, because I thought that you were looking for the actual, like the substitution kind of mechanism for chlorotoluene when we
No
add.
substitution. The reaction we are doing today is not substitution. The reaction we are doing today is actually oxidation.
Oxidation.
Yes.
Okay. All right. So, well, I already submitted my lab notebook, and I thought that the mechanism you wanted was actually the drawings in the lab manual. So I did include that. So, I mean, it's
Okay,
not the
perfect.
mechanism anyway,
It's not
but
the mechanism, but it's the sample reaction.
right. Okay. Yeah, that's what I put
Yes, good.
in the
Those are
same
reactions.
format. Okay. Thank you.
You're welcome. Okay, any other questions before I go over the experiment? Is there any other reaction questions? Any concerns? Any questions? No questions?
Oh, I have one more question. At the end of the experiment, can you just briefly go over the theoretical, how to calculate theoretical yield again? Because I know that a lot in Orgo 1 with you, but I just want to make sure I understand it again.
Sure, I will.
Thank you.
You're welcome. Okay. Okay, the Blackboard Collaborate, it might be is using a phone. If it's in the within the Black D2L, there should be no problem. The link is not working, or could you find out if the link is not working, or is it the internet connection? If the link is not working, just email the link, send the link via the text or what you have, and then hopefully that would help. If it's the internet, we don't have a solution. I don't have a solution for that. So, okay. Now, if you don't have questions, now I have questions for you. Michael, are you here? Yes, good. Could you tell me what is the reaction in this experiment? What experiment we are doing today? What's the major reaction in the experiment today? You can use the chat or mic, either one. Okay, better. Now I have only 2 windows open, hopefully. Okay, who was answering the question? Michael. We see what you have. Oxidation would be the reaction. So is the oxidation of chlorotoluene with potassium permanganate, oxidation of the side chain or aromatic side chain aromatic compounds. Perfect. Okay, the reaction is oxidation of the side chain of an aromatic side chain. The set of reactions that it shows in the lab manual is indicating that as long as you do have alkyl side chain to the aromatic ring and the alkyl group, if it has benzylic hydrogen. What is benzylic hydrogen? It's the hydrogen in the benzyl position, and that is the carbon, the first carbon attached to the benzene ring. So if we have benzylic hydrogen, regardless of the size of the alkyl group, the product of oxidation with permanganate is going to be benzoic acid. So if you have methyl group, ethyl group, isopropyl or propyl group, the product is going to be single product of benzoic acid. This is something that you will also learn in lecture. If there is no benzylic hydrogen, so you have this carbon attached to the benzene ring, and the other three groups are occupied by methyl group, so there is no hydrogen on this carbon directly attached to this carbon, there would be no reaction. Okay, next. Karina, could you please tell me what's the purpose of experiment today? The purpose for experiment is? Yes, Karina, could you tell me the purpose for the experiment? Melissa, what is the purpose for the experiment? The purpose for today's experiment. Why do we do oxidation of the chlorotoluene? To identify the unknown chlorotoluene sample based on the melting point. Okay, so you can use the chat to respond to any of the questions. To find the unknown, okay, to find the unknown. So the answer given by Karina, actually, this is good. Yes, Victor, different or same answer?
No, Professor, it's just a question about this paragraph here about if an OH group or NH2 group is directly attached to the aromatic ring, the benzene ring will be destroyed. So this paragraph right here, I'm trying to figure out what it looks like in a structure, but I'm not seeing it. Does that mean that we don't have carbon attached to the benzyl ring, OH, and there's no reaction? Same as when you have a non-benzylic hydrogen? Is that what it means? And that over-identification of an unknown chlorotoluene. The presence of halogens, nitronel alkoxide groups. That paragraph. What happens when you have an OH or NH2 group directly attached to the aromatic ring?
Okay, if you have an OH or NH directly attached to the benzene ring, how would that affect on the oxidation?
It says, but if an OH group or NH2 group is directly attached to the aromatic ring, even the benzene ring will be destroyed. In this experiment, we'll be using oxidation to side chain to identify unknown chlorotoluene. So I'm just wondering why you mentioned this in the book.
Okay, it's a good yes, it's a good question. The problem is that you learn about aromatic compounds after in lecture later, but when that chapter is covered, you will see that if you have an OH group or NH group attached directly to benzene ring, those are activating group. The aromatic ring is very stable. So the reactions shown there is showing that only the side chain would be affected. So that means that the ring is going to be protected. So the controversy to that, so the only exceptions would be if you had the OH group attached directly, it will make the benzene ring active. As a result, the the benzene ring can actually react with the permanganate, and it can be destroyed. So what is telling you that benzene ring is very stable. That's the reason I explained that benzene ring is very stable and it does not react. The only thing that reacts with the permanganate is the side chain that would react with the condition that if you do have a hydrogen in the benzylic position, but if you have OH attached to it, your benzene ring is going to be activated enough to start reacting with oxidizing agent of permanganate. Very good.
Thank you, doctor.
You're welcome. Okay, so the response was, we are trying to find out, and I'm going to ask one more question, that chlorotoluene is liquid. You said that we are finding out, or we are identifying the unknown based on the melting point of the product. Melting point is physical property, and it is valid point. You can identify a compound based on melting point. Boiling point is also physical property. If you measure boiling point, you can identify unknown. And Cindy, can you tell me why can't we use the boiling point of the unknown and determine what the unknown is, instead of going through all this trouble today? Cindy, are you here? Cindy, first let me know if you are here, you can hear me, and then answer the question. Perfect. Could you tell me why we cannot use the boiling? Why can't we use the boiling point directly instead of going through the reaction and measuring the melting point of the product? Denise? Yes, could you answer the question, please? Okay, because, let me go to the chat. Cindy, because their numbers are too close. Yes, Cindy, that is correct. The numbers are too close. So if you look at the table is provided here, the boiling point for 2-chlorotoluene. So basically, you're not starting with the unknown that is pure unknown compound. But you already know that it is toluene, and you already know that there's a chlorine attached to the toluene. The only part that is unknown to you is either the chloro group is attached to carbon 2, which is this position, that's the ortho position. So is it 2-chloro? Is it on this position, which is a 3 or meta position, or if it's attached to 4 or para position? Because if it's attached to the other side and position 2, it would be the same thing as if it was attached to the right side, and it would be 2-chlorotoluene. So the question is, our chlorotoluene, is it 2-chloro, 3-chloro, or 4-chloro? The boiling point difference, you have 158, I'm just taking the average, 161 and 163. It's too close to call. So since the boiling points are too close, we cannot use the boiling point data, but confidently to find the name for our unknown. So in this situation, and this experiment is a perfect start, because you are going to finish with this idea at the end of the semester. If the melting point of a compound or boiling point of a compound that you are finding is too close to another compound, you cannot use that melting point. Is data, it's kind of a primary data, and you need like a secondary, or you need a confirmation for that. So what you do in this case, we just call it oxidation. We oxidize, we change it to solid compound. And since it's chlorotoluene, the CH3 is going to be oxidized, and you have the balance equation here, and that's what you are using for your calculation for percent yield and theoretical yield also. I'm just mentioning that. So you do have chlorotoluene going to chloro. benzoic acid. Benzoic acid, because it's more polar compound, is solid at room temperature, so you are going to measure the melting point of the product. When you measure the melting point of the product, if it is within the 138 to 140 area, then it's going to be 2-chlorobenzoic acid. That means your reactant or your unknown was a 2-chlorotoluene. If the melting point is in the range for 3-chlorobenzoic acid, that means that your unknown is not chlorobenzoic acid. Your unknown, it used to be a liquid that is called 3-chlorotoluene. And same thing for the 4-chloro. So the melting point for 4-chloro is much higher, and it's going to be, if the melting point is around 240, that means your compound is 4-chlorotoluene. There was a question in the pre-lab. If you find the melting point to be 180 or 190, what would be your unknown? Did you find that answer to be, what would be your unknown? And how would you justify it? Okay, Therese.
Good question, or are you going to call on me?
Anyone can answer that question.
Four
3-chloro is going to be 4-chloro. So how would you justify that it's going to be 4-chloro? Ahmed, you have the product is not pure.
Pure or it was not dry.
Okay. Impure sample of 4-chloro. Okay, Michael, that is correct. Impure sample of 4-chloro. So because it's an impure sample, but you still can say which compound it would be, because impurity would always lower the melting point, and it should never increase the melting point. So if it's 180, that is higher than the 2-chlorobenzoic acid, which is a 140, and is higher than 3-chlorobenzoic acid, which is a 157. So yes, it is colligative property and is going to lower the melting point. So why is 180? That means the melting point is very low compared to the actual value or the theoretical value, because the compound is highly impure, or it is wet. If it's mixed with the solvent, instead of melting your sample, you are basically dissolving. What temperature does it take for salt to dissolve in water? You add salt and it dissolves in water. What temperature does it take for sodium chloride or table salt to melt? 800 degrees Celsius. So if the sample is contaminated with solvent, basically it dissolves. And as a result, it's going to melt or disappear at very lower melting point than compared to the actual. So because of that, the compound is 4-chlorobenzoic acid would be the choice, and mapping back to choice of the unknowns is going to be 4-chlorotoluene. If the sample is wet, is going to weigh more, but if it weighs more, it's going to affect. That's another good point. It's going to affect the percent yield. Percent yield is determined based on the mass, but melting point is determined based on the purity of the sample. How pure is the sample? Remember, experiment 1 in organic 1, purpose for melting point determination is to identify or determine the purity, identity and purity of the sample. So if it's lower than what it should be, it means the sample is not pure. Your sample, if it's wet, the weight is going to be affected also. But sometimes you can catch that just by measuring the mass. Other times you cannot, because if you lose the powder during filtration and then your sample is wet, you lose the powder, the product, then the mass would be lower. and then you don't dry it well, is wet, so it weighs more. So for like 1045 lab, it would be all right. But for organic lab that we depend on like the melting point to determine how pure your sample is, or if we use IR to see what are the peaks, if any peak shows up corresponding solvent, then we know the sample was wet. So that kind of defeats the purpose of being very concerned about the percent yield. But I still want you to calculate the percent yield, because calculating percent yield is, you know, showing the calculation, understanding what's limiting reactant, what is the excess compound, because we do have a lot of practices and the application for that part. Okay, next question. Gian. So I'm sorry, just let me just make sure that everyone understands the purpose for the experiment today, why we are performing this experiment today. The reaction is oxidation of the side chain aromatic compound. The oxidizing agent is the permanganate, and the purpose of the experiment is to find the name for the unknown. Is it 3, 2, or 4 chlorotoluenes? Now, Gian, what is the limiting reactant in this case, in this reaction? And what's the excess compound? First of all, let me know if you're here. Okay, thank you. And can you tell me which one is limiting and which one is the excess compound? Sometimes it's kind of very obvious, or is written in the procedure. It says this is the limiting reactant. Other times when you read the procedure, you find out which one is the limiting reactant and what should be your limiting reactant in this case, and what is the limiting reactant and which one is the excess compound. Gian, the MnO2 is remaining. So MnO2 is a product. KMnO4 is the one that is left over, so that is the excess compound. Chlorotoluene, or your unknown, is going to be the limiting reactant. Which line of the procedure help you to determine that KMnO4 was excess? How would you know? How do you know? There are two ways. Either you do calculation, you divide the mass of permanganate to molar mass of permanganate to see how many moles of permanganate you use, and then you find the moles of chlorotoluene, and if it's a 1-to-1 ratio, see which one is lower, and that would be the limiting reactant. From the experiment, even if you don't do the calculation, from experiment you can find out also when you are reading the procedure. What made you or help you to find out KMnO4 is excess? Any idea? Anyone? Natalia?
Not sure. I would say when
Yeah.
you see that the purple ring in paper, that's an indication that that's an excess, or at one point that's the indication, and you have to
Okay.
see that.
Yes, exactly. At one point is telling you to use sodium bisulfite to remove the excess of potassium permanganate. So if at one line of the procedure it says to remove the excess of potassium permanganate, that means you have used extra potassium permanganate. That's a good observation. Okay, Jones, we talked enough about the reaction. Now let's look at the lab techniques. We used reflux in this reaction, in this experiment. And John, are you here? Yes, you are here, right, John? So could you tell me what is reflux? Yes, Jones. Could you tell me what is reflux? Under what condition you would use reflux for a reaction or in a technique? Under what condition you are using reflux? When you want to remain at the reaction, right? When you want the reaction to stay at high temperature for a long period of time. Very good. If the reaction requires heat and the heat is like for 1 minute, what you could do, you can place the reaction mixture in a beaker and you heat it up to boiling for 1 minute, and then you remove from heat. But when the reaction calls for 1 hour high heat and you want to maintain the high temperature, then if you do that in a beaker or open container, the solvent evaporates and your sample or your unknown is going to decompose because the temperature is going to go higher, because if the solvent evaporates, then temperature is not going to stay at the boiling point of solvent. The temperature is going to go much higher. It goes to boiling point of your sample, so it can decompose the reaction mixture or the reactant. So what you do, you are going to set up the reflux the way that is showing on the screen now. We have a hot plate. This hot plate is not providing the heat actually. It has 2 knobs. One is for heat, one is for stirring. The heating mantle that fits the 250 ml boiling flask is used for the heat. And the heat is going to be adjusted using a power regulator, not shown on the picture, but you see that in the video. The stirring bar, the magnetic stir bar is going to be placed inside the flask, and the stirring knob of the hot plate is going to be turned on. While it's boiling, it's going to be stirred by the magnetic stir. And what is the purpose of that stirring? Anyone? Why do we have to keep stirring? It's very similar idea of using boiling chips. When you are heating up
the heat evenly. That the purpose of
yes, very good.
Much like a calendar, when you cook, you have to stir so you can, pretty much hit all the molecules evenly.
A smooth boiling, gentle boiling, and even distribution of the heat to avoid bumping. Basically, boiling chips, that's what it does. If you use boiling chips here, boiling chips, because your compound, one of the product is solid. MnO2, manganese dioxide, is solid and is going to form, a lot of that is going to form. As a result, that compound with the boiling chips is going to settle and is not going to stir. But when you use the stirring bar here with the strong magnet or magnetic stirrer, is going to spin the bar and makes the solution like constantly moving. As a result, is going to avoid bumping. If you don't use that, very, it's highly possible that you are going to get like splash of the whole, solution or mixture from the top of the condenser. And sometimes when students are in the lab, they witness that we have like spots, the brown spots in the ceiling. I think I showed that. I don't know. I'm not sure. But I usually show that to students in the video, that if you don't keep the stirring on and constant stirring, a bumping can make the splash, and you can lose the product. So to avoid that, you are using magnetic stir. So the setup for reflux is very similar to setup for simple distillation, with an exception that here you don't want to collect the condensed vapor. You want to put the condenser upright, in an upright position, that when the vapor condenses, it drips and it goes back into the solvent. So you maintain the level of solvent. You don't want to dry out the solvent. That's why you are using the reflux in this case. Yes, Victor. Question or answer? Yes.
You mentioned at one point that condenser has like a little field that you don't put in. You leave it open or semi-open. Is that correct from the video?
From the reflux and reflux and both yes, both reflux and distillation, it has to be open container, because if you close it, the build-up vapor increases the pressure and it can cause exploding of the glass.
My question is, if you have that thing open, wouldn't the vapor leave the condenser, or is it like a certain length that, you know, given the temperature and the length of
what you see, sure, when you have the vapor moving up along the condenser, if you notice that the vapor is coming up, because it's water, I mean, you might see the vapor coming up, and that vapor is not very dangerous. Sometimes I let this condenser to act as an air condenser. Other times I would make sure that the rubber hoses are attached. Water goes from the bottom part and then it comes out from the top opening. Water comes out. The circulation of the water here, it would make the vapor to go back. Now, if the circulation of the water is not sufficient, you might see vapor going up, and that's lose up the solvent, or with the product sometimes. You have to avoid that also. So what you do, you lower the heat here for the heating metal, you lower the setting for the heat to avoid overheating. You don't want overheat. You don't want to generate too much vapor, because if you generate too much vapor, then the condenser cannot condense everything back, and that would be a problem. So you want to make sure that you are. Yes.
You have to where the condenser can keep up with the vapor being generated, so it can convert it back can condense it back to the liquid, to the solvent, before it escapes.
Exactly. Okay, there was another question regarding, so this is the reaction that you are using for your calculation for percent yield. For the question that you had, how do you calculate theoretical yield? I'm going to share with you the announcement that I sent or is set up. And for that, I have to go to the course, and I'm going to show you the announcement here. And I will explain from the announcement. It doesn't show here, so I'm going to make it visible to class. This one. Bring it to the top. Okay. To calculate the percent yield, based on the procedure, you are starting with 1 milliliter of the chlorotoluene. The density for chlorotoluene is 1.08 gram per milliliter. So you use the volume and density to find the mass for chlorotoluene, which is your reactant. From mass of the reactant, you go to the moles of reactant. How do you convert mass to mole? If you have the mass of a compound, how do you convert that to moles?
Molar mass in periodic table.
You divide the mass by molar mass. You can search for the molar mass. Molar mass may or may not be provided in the experiment. In the ebook for organic 2, there are some values that I do not provide, and I want to make sure that students actually are searching for those information. And those are constant numbers. It's just that, you know, you search for them. So when you have the moles for the reactant, then using the mole ratio, you look at the balance equation. The equation that I just showed you, chlorotoluene to chlorobenzoic acid, was a 1-to-1 ratio. So it's a 1-to-1 ratio, but you still want to show that in your calculation. That's how you're getting the moles of chlorobenzoic acid. When you have the moles of chlorobenzoic acid, use the molar mass of the product. This is like general, but in this reaction is the molar mass of chlorobenzoic acid, and you convert that to mass of the product. When you find the mass of product, which is calculated, and this is called the theoretical yield, or the mass of the product, the formula that is shown down here is basically summary of the 3 steps that you have up there. You have the mass of the reactant, you change to moles of reactant. When you have mole of reactant, you change that to mole of product. From mole of product, you change to mass of the product, and that is the grams of product or theoretical yield. When you have theoretical yield, you have the actual. What is actual? Actual yield is what you get on the scale, on the using the balance, the difference between the mass of filter paper and the product, and you subtract the mass of filter paper, you get the mass of the product. And that's how you calculate percent yield. You also measure the melting point for this experiment. Melting point is used to identify the unknown, the name for the unknown, and the 3 choices that you have is 2-chloro, 3-chloro, or 4-chloro. And then you have the percent yield is just to see how you did the experiment or being able to do the calculation. The table for data, similar to the ones that I showed you beginning of the discussions. You have like a small table, items you are recording over the term of the procedure, and then the numbers with the values and the units recorded on the right side. Then you use the data to do your lab report, to finish your lab report. Is there anyone who has not answered any question yet? Okay, those your answers are recorded, Christopher. Brianna, but I haven't actually had any answers. Ahmed, I didn't call your name, but you did answer. Same thing for Christopher. Yes, you did answer the questions. Taylor, you did answer questions. I did not call everybody's name, but some of you actually answered the questions, and I have it. That's okay. That's okay. Next time for the. Okay. Any questions that you might have for me?
Doctor, I have a question regarding the lab report, and I might have more on Friday for office hours for now. So when I'm writing the lab report, this is everything in my own words. Okay, I'm gonna base off my content from the video as if I were in the lab. This is my first
Yes.
time taking remote learning for lab, so
Yes.
it's very new to me. So any observation that I have from the video as if I was doing the experiment, with the numbers that we get from the video, well, from the video, that's the only place we're getting numbers from, right? Or actual weights, and from the pre-lab and from the book. So the numbers that we use for amounts for 50 ml of water, the 3 grams of permanganate that we use, those are the numbers that we're using for the lab report. There are no other numbers. I'm not running the experiment myself.
Okay. If it's anything like a procedure, you don't have to write in the lab report. You only write the valuable or major findings of the experiment that is going to help you to identify, like the melting point of the compound that goes to the abstract and to the conclusion. But on the table that for your data, you write the mass of the reactant, mass of the product, and melting point of the product. But you don't have to write every single numbers, like how many milliliters of water, how many grams of sodium, potassium permanganate, because that's part of the procedure. You don't have to bring the procedure into the lab report. You just have to explain how and why you're doing the experiment based on the information you have in the lab manual. Okay, one question, Brianna. Brianna, one question for you. The purpose of using number 42 paper, filter paper, the Wattman filter paper number 42. Could you tell me why we don't use P8? Because the other type that we have in the lab is P8. What's the purpose of this? Okay, and Olavia, if you're here, you can also help. I am. Olavia, okay, good. Julia, undesired component, isolate impurity, pore size, okay, pore size and the qualities, okay. So which one is a better quality? The 42 or 8? 42. 42 is more, it's more efficient filtration because the pore sizes are smaller, the paper is thicker, and when you watch the video, you realize that how much of you basically end up as an end product. You end up with the mud, and then you're trying to filter the mud and get the liquid, pure liquid only. You want to get the yes. You want to get the product, the solution only. Okay, you want to get the solution only. The solution that is filtered, this one would go to anyone else who did not answer the question. Who has not answered the question? Okay. When you separate that liquid using filter paper, the aqueous solution that you have, what is mixed with that solvent in there? With your solvent, what is mixed? Is it the benzoic acid in the solution form? Or what form of benzoic acid would that is there? And the reason I'm asking, because your final product is solid, right? And the name of your final product is benzoic acid. So if your final product is benzoic acid, how do you separate that in that liquid? When you separate the liquid from the mud, from the MnO2, what is in there? It must be a soluble form of a benzoic acid. Is a soluble form of benzoic acid. What form of benzoic acid is soluble in water? Benzoic acid is not soluble in water at room temperature. Benzoic acid is actually solid. So if it's in the aqueous solution form, what form of benzoic acid is that? When you separate that liquid, you are going to add HCl in order to change it to solid. That's in the procedure. So before adding HCl, what form of benzoic acid do you have? In the aqueous solution. Is the aqueous solution actually is not liquid. If it's liquid, that means has been melted. But if it dissolved, that means it's an aqueous solution. What form is water plus what? Benzoic acid itself. Benzoic acid doesn't dissolve in water. So when it's if it's clear solution passing through the filter paper, it's water plus a sort of benzoic acid, but it's not the benzoic acid. It's a sort of benzoic acid. Water and is basically is water and the sodium benzoate, because you add sodium hydroxide to the reaction mixture, and when benzoic acid forms in the reaction mixture, you said sodium benzoate or you said sodium thiosulfate? Said sodium thiosulfate, I believe. Bisulfite. It's not the bisulfite, it's sodium benzoate. Yes, sodium benzoate. So that's what you mean? Okay. If that's what you meant, then it's fine. Bisulfite, no. Sodium bisulfite is used to react with permanganate. But benzoate is the benzoic acid that has lost hydrogen, and instead you have a sodium there. When you have a sodium benzoate is a salt, because you have the anion, and ATE stands for like ionic compound, basically. A sodium benzoate is ionic compound and is solid at room temperature. I'm sorry, is soluble in water. Any compound, that's good. Any compound that contains sodium is going to be soluble in water. So when you have sodium hydroxide and benzoic acid, when it's produced in the reaction mixture, when your reaction is taking place, that benzoic acid reacts with sodium hydroxide and it changes to sodium benzoate. And sodium benzoate is soluble in water after you filter it. After the filtration is done, when you add HCl reacts with sodium hydroxide, it removes the sodium hydroxide and it changes the sodium benzoate to benzoic acid. Then you have your benzoic acid, solid benzoic acid, and that gives you a white powder that you would filter and you separate it. Okay, attendance. Brianna?